So in this section, we will discuss the so-called image measures. And to have an idea of what we are heading to, let us consider the following situation. So let's start, let's say, with a measure space X sigma mu. So X is a set, sigma is a sigma algebra on X, and mu is a measure on X, defined on the sigma algebra sigma. Suppose that we have a mapping from X to Y, say F. And we would like to define a measure on Y out from the mapping F and the measure mu. And this is our goal. Well, to have a measure, one needs a sigma algebra on Y. So suppose that T is also a sigma. It's a sigma algebra on your space Y. Then we would like to define the measure, let's say, of a subset E. So here, suppose that this is E and this is in the sigma algebra T. We want to consider, or we want to define a measure, let's say nu, of E. Well, to do that, one might look at the, let's say, inverse image. Say this is F inverse of E. And in this case, okay, if we want to apply the measure mu, this must be in sigma. So if that is the case, then it is, well, reasonable to say that we define the measure nu of E to be the measure of the inverse image. Okay. So based on this discussion, there's a need that the inverse image of sets in the sigma algebra on the domain on the codomain Y must be an element of the sigma algebra, in this case sigma, of the domain. So again, if you have an element E in the sigma algebra T in Y, then the inverse image must be an element of the sigma algebra sigma on X in order for this to be well defined. Okay, still we're not saying that this is a measure, but this is a possible candidate. Okay, so the requirement that F inverse of E in sigma is what we call a measurable function. Okay, so to formally state that one, so let X sigma and YT be measurable spaces. And by this, we mean that sigma and tau are sigma algebras on X and Y respectively. So here, a pair, so that's a set, and a sigma algebra on a set is what we call a measurable space. Well, if to make it a measure space, then we need to define a measure on these two measurable spaces. Okay, so a map, let's say f from x to y, will be called measurable if f inverse of tau is a subset of sigma. More precisely, this means that f inverse of E is an element of sigma for all E in tau. Okay, so elements of a measurable space, in particular the sigma algebra, will be called measurable sets. So this means that a measurable set in Y is the inverse image under F is also measurable in sigma. So in order for your function F to be measurable. So this is the requirement that we have mentioned here. So if you have a map F from one space to the other, we say that that map is measurable if an element E, if for any element E in the sigma algebra tau in Y, the inverse image under F of that set is an element of the sigma algebra in X. It should be emphasized here that measurability of a function has nothing to do with a measure. Okay, so here you only need the sigma algebras of the domain X and the codomain Y. So as an example, simple example would be, let's say, the characteristic functions on measurable sets. And suppose that A is in sigma. Well, to emphasize that what sigma algebras are we referring to, then we say that this is sigma tau measurable. Okay. Because there can be different sigma algebras on a set, on a given set. Going back to this example, so the characteristic function here is, let's say, measurable with respect to, okay, so let's say, let us take the Borel sigma algebra on R. Indeed, one can check immediately depending on whether 0 or 1 is in the set E. So if 1 is in E, however, if 0 is not in E, then the inverse image must be the set A. On the other hand, if 1 is not in E and 0 is in E, then it must be the complement of A. If both are elements of E, then you get the whole space X, because the image of the characteristic function is the set containing 0, 1. If neither 0 nor 1 is in E, then this is the empty set. And take note that since A is in sigma, these are all in the sigma algebra sigma. In fact, this is true not only in Borel sets, but in fact on all subsets of R. Hence, for all Borel sets as well. Okay, so that's our example. So the characteristic function of a measurable set is measurable with respect to the sigma algebra on X and the Borel sigma algebra on R. In fact, you can replace the Borel sigma algebra by any sigma algebra. Okay, so another example would be the composition of measurable functions. So now let's say we have 3 measurable spaces. So I have a map F from X to Y tau, and then a map G from let's say U or Z U. So these are, say, measurable spaces. If your map F from X to Y and your map G from Y to Z are, let's say, sigma tau measurable and tau U measurable respectively, then the composition, so that's the map from so that's the map F followed by G. So this is now a mapping from X to U to Z, I should say. Then this one is measurable with respect to the following sigma algebras, namely X and U. Okay, so let's say just to have an intuition, say this is X, this is Y, and let's say this is Z. To prove this is your map F, map G. This will be your composition. So for, let's say, for each E in U, so you take, let's say, a measurable set E. If you take the inverse image, under G, so this will now be G inverse E. And if we apply the measurability of G, the inverse image must be an element of T, that's the sigma algebra, okay, in Y. And hence, since this is in T, if I take the inverse image of this inverse image of E under G, this must be in sigma. So you further take, let's say, the inverse image of this under F, then you will get F inverse of G inverse of E. And recall from the definition of the inverse image that this is the same as the inverse image of the composition GOF of the set E. And this implies measurability of the composition. Okay, so the composition of measurable sets is again measurable. Now, to simplify the task of proving a measurable map, if you know a generator on your sigma algebra on the codomain, then you can use that as a way of proving an alternative way of proving measurability. Okay, so to be precise, so suppose I have two measurable spaces, x sigma and y tau. And T is generated by some collection E. So for some E, which is a collection of subsets, of course, it should be Y. Then the map F from X to Y is measurable with respect to these sigma algebras if and only if, so you can use this as an alternative definition, if and only if the inverse image of the generator is contained in a sigma. So that is F inverse of E is in sigma for any E in tau. Or I should say for any E in script E. So instead of verifying or checking the inverse images of all elements in the sigma algebra tau, it is enough to look at the inverse images of elements of the generator script E. The proof is quite straightforward. So for this direction, so suppose that your map F is measurable. Okay, since T is generated by E, so therefore it contains E. This implies that the F inverse of this collection is a subset of F inverse of T, and measurability implies that this is a subset of sigma. So that's this direction. On the other hand, okay, so suppose that F inverse of E is a subset of sigma. So our goal is to show that F is measurable. So we need to show that F inverse of tau is a subset of sigma. Okay. Take note that the collection, let's say T prime, defined the following way. So this is the set of all, let's say, F in a T having an inverse image. Okay. So let us say, let us replace the notation. Let's say G in a T such that the inverse image of G is in sigma. From our previous discussions, since sigma is a sigma algebra, applying the properties of the inverse images, this is a sigma algebra on X, okay, that contains the script E, the generator. Since, take note that this property here is satisfied by elements in the generator. So thus, if this T prime is a sigma algebra that contains E, then it must be larger than the sigma algebra or possibly equal to the sigma algebra generated by E, since this one is the smallest sigma algebra containing E by definition. But we know that this is T. And this implies that the inverse image of T is a subset of the inverse image of T prime. But since elements of T prime have inverse images that are in sigma, this is a subset of sigma. And that's the end of the proof of this theorem. So therefore, F is measurable. Okay, so as an application of this theorem, so if I have, let's say, a function from Rn into Rm, so we have two Euclidean spaces with possibly different dimensions. If this is continuous, then F is measurable. So if you want to be precise, what do we mean by this? So let's say Borel measurable. In other words, so with respect to the Borel sigma algebras on Rn and on Rm. So these are the sigma algebras for the Euclidean spaces in the domain and on the codomain Rm. Okay, well, to see this, let's say let tau to the n be the open sets in tau or in Rn. Okay. Oops. Sorry for that. So open sets in Rn. Okay, we want to do this both for n and m. So let's say tau d is the collection of open sets in Rd. D here is either n or m. Now, to show that this is the case, according to our previous theorem, since the open sets generate the Borel sigma algebra on Rn, then it is enough to establish this, okay, in the case of open sets. So in other words, we want to show that the inverse image of the open sets in the codomain, so that's tau m, is a subset of the Borel set in the domain. So this is your sigma. Okay. So to have the correspondence in the previous theorem, you can think of this as your sigma. You can think of this as your t. And you can think of this as your script e. So this will be your sigma. This is precisely this property here. However, this follows from the fact that the inverse image of an open set in the codomain Rm by continuity are open sets in the domain. Okay, so with this, take note that this, of course, is contained in the sigma algebra generated by tau n, and this is nothing but the Borel set in Rn. And that is what we would like to show. So therefore, a continuous function between Euclidean spaces is Borel measurable, that is measurable with respect to the Borel sigma algebras. Okay, so those are some discussion on measurable functions. Now, going back to this discussion a while ago, okay. We now discuss how to construct the measure on Y. And this is the content of the following theorem. So let's start with a measure space, X sigma mu, and a measurable space Y tau. So that is Y is a set and tau is a sigma algebra on Y. If this function f is measurable, then the function f sub star mu from the sigma algebra tau to 0 to infinity defined by. So how do we get the measure with respect to this function? So E here is an element of T. Okay. So we define this as the measure of the inverse image of E. So this is a measure on a Y. And we call the triple Y T F sub star mu an image measure space. If you want to be precise, the image measure space corresponding to F and mu. And this theorem is our motivation, or the motivation of this theorem follows from this discussion last time. Okay, so the proof is quite simple. You just apply the measurability of, let's say, F and the fact that mu is a measure. I would like to emphasize here that since F is measurable, then this is in sigma. So therefore, the right-hand side is well defined. Okay, so for the proof, need to verify two things. So let us take the value of this under this function, the empty set. So this is by definition mu of f inverse of the empty set. The inverse image of the empty set is empty. Since mu is a measure, this is 0. On the other hand, if we have, let's say, a sequence of pairwise disjoint sets in the sigma algebra T or tau, so if this is pairwise disjoint, then so is the collection of inverse images. Since, okay, we just apply the properties of the inverse image of or the intersection of inverse images of two sets. So this is equal to, so the inverse the intersection of the inverse image is the inverse image of the intersection, and this is equal to empty, the empty set, provided that the indices are distinct. We know that the inverse image of the empty set is empty. So for distinct indices, this is also empty. And by measurability, this is a subset of sigma. So this here is by measurability of your function f. Since E sub n is in tau, then the inverse image must be in sigma. Okay, so everything has been set up. We now compute the value of this union, of this pairwise disjoint union with respect to f sub star mu. The first step is basically the definition of f sub star mu. However, the inverse image of the union is the union of the inverse images. And since the inverse images are pairwise disjoint, applying the additivity of your measure, this is equal to the sum of the measures of the inverse images. This is nothing but the sum of the f sub star mu of E sub n by definition. So this proves the countable or sigma additivity of f sub star mu. And therefore, this is indeed a measure on a y. Okay, now let us consider, let's say, a measure space x as sigma mu, and I have a map, let's say, from x to y, and I have this as our a sigma algebra tau. From the previous theorem, I can define an image measure. So this is an image measure space. If we have another function, let's say g, that maps this image measure space into another measure space, let's say Z, U. One can, of course, define, again, the image measure of this measure with respect to a G. So that would be G star F sub star mu. This is again an image measure space. However, we can have, or we can look at the composition F followed by G. So this is now a map from X to Z. I can also construct the following image measure space under this map. So now we take the function to be this composition. Okay. Of course, here F is measurable. G is also measurable. We know that the composition of two measurable functions is again measurable. So applying the previous theorem to the composition, you have this. However, these two constructions coincide. This is what we call the transitivity of image measures. So you can either take the image measure with respect to the composition, or you take the image measure iteratively with respect to F followed by G. Well, to see this, if you take a set E, take note that, of course, these are your, should I say, this should be in U, okay, because that would be your sigma algebra. Let us compute, let's say, the image measure with respect to the composition. By definition, should be a mu E here. So by definition, this is mu of the inverse image of the composition of E. You apply the properties of the inverse image, so this should be F inverse of G inverse of E. So take note that if I want to pull the function out, so I need to take the function, not the inverse image, put a subscript, and you have this. Again, pulling this out, we would have G, put a subscript. So here we are just applying the properties or the definition of the image measure. Okay, so that is, if you want to pull out this one, you need to remove the notation for inverse image and put a subscript. So that is somehow the algebra in doing these image measures. Since this is true, for each E, this implies that the two image measures, GOF star mu, is the same as G star mu star. So you can distribute the star in this case. And of course, remove the notation for the composition. So This is what we call a commutative diagram, because either you go on this path for the image measures, that is F followed by G, you obtain the same measure by going directly using the composition. In the next lecture, we will specialize the discussion in the case of Euclidean spaces.